In the world of high-performance computing, there is a common assumption. If one CPU is fast, two must be twice as fast. We buy dual-socket servers, expecting linear scaling for our databases, web servers, and build runners. However, modern hardware hides a complex secret known as NUMA, or non-uniform memory access. On paper, a server with two sockets looks like a unified pool of resources. In reality, it is two distinct systems, bridged by a narrow, invisible straw. When your software isn't aware of this boundary, performance doesn't just plateau, it can actually drop below what a single-socket machine would provide. Today, we are going to peel back the heat spreaders and look at why the physical distance between your processor and your RAM is the most important metric you aren't measuring. To understand the bottleneck, we have to look at how memory is physically wired. In older architectures, all CPUs shared a single controller to reach RAM, but as core counts exploded, that controller became a massive traffic jam. The solution was to give each CPU its own dedicated memory controller and its own local bank of RAM. This grouping, one CPU socket and its directly attached memory, is what we call a NUMA node. When a core on socket 0 needs data from its local RAM, the path is short and fast. This is local access. It is the gold standard for performance. But what happens when that same core needs data that happens to be stored in the RAM attached to socket 1? It has to ask the other CPU for permission to use its memory controller, creating a detour that changes everything. To bridge these two nodes, manufacturers use high-speed interconnects like Intel's UltraPath Interconnect or AMD's Infinity Fabric. While these links are incredibly fast, they are not instantaneous. This is where remote access comes in. When your application running on CPU 0 reaches across to Node 1's memory, it incurs a hop. This hop adds significant latency, often between 30 to 100% more than a local request. In a world where we optimize for nanoseconds, this is an eternity. But it's not just about the speed of a single request. These interconnect links have limited bandwidth. If every core on socket 0 is constantly fetching data from socket 1, the interconnect becomes saturated. At this point, your multi-thousand-dollar server begins to choke on its own internal communication, leading to the erratic performance dips that haunt system administrators. The real danger isn't the hardware, it's software that doesn't know the hardware exists. By default, the operating system scheduler tries to be helpful. It sees 64 cores and treats them as one giant bucket. If node 0 is busy, it might move your database process to node 1. But if that process already allocated its memory on node 0, it is now stranded. Every single memory instruction now has to cross the interconnect. This is called remote memory thrashing. Your P99 latency spikes because the thread is literally waiting for data to travel across the motherboard. This is why a single socket server with 32 cores can often outperform a dual socket server with 64 cores for memory-intensive workloads like Redis, Postgres, or large-scale Java applications. In a single socket system, every access is local by definition. There are no hops, no interconnect bottlenecks, and no surprises. So how do we fix this? The answer is NUMA pinning. We can tell the operating system, run this process only on node 0, and only use memory from node 0. In Linux, we use tools like NUMA control to enforce these boundaries. By siloing our applications into specific NUMA nodes, we eliminate the interconnect hop entirely. Instead of one large, slow server, we treat the machine as two smaller, independent, lightning-fast servers. High-performance databases like MongoDB and SQL Server have built-in NUMA awareness for this exact reason. When you're architecting your next cluster, remember, more sockets isn't always more speed. If your workload can fit within the core and memory limits of a single socket, it will almost always run faster and more predictably than if it were spread across two. Complexity has a latency cost. Don't pay it unless you have to.